not so large seminar, but I was told that KAIST is now the second university of Korea after Pohang, so I'm really honored to be here. Okay, so I will talk about contact homology.
Second what?
Second university of Korea.
You mean the best?
Yes.
Second best?
Yes.
What, second best? Oh, okay.
Second best, but I'm just Pohang. Yes. I'm in number 3, so.
No problem.
Okay, so let's start with the definition of contact manifold. So a contact manifold is an odd-dimensional manifold with a maximally non-integrable field of hyperplanes. And so usually you say it in this way, the field of hyperplanes is psi, and then locally you can describe it as a kernel of a one-form alpha, and this one-form alpha should satisfy this non-degeneracy condition. And geometrically it just means that this field of hyperplanes, well, here's an example, twists in a certain way. So this field of hyperplanes psi is called the contact structure, and alpha is called a contact form. And maybe I should point out that this form is, at this point, is just one example, but later this will kind of be the universal contact structure in some sense. Okay, so the first observation to make is with this data is that psi d alpha is the symplectic vector bundle. And from that you deduce the following proposition. So if I have an integrable submanifold of this contact distribution, then the dimension of this integrable submanifold is at most n if the dimension of the contact manifold is 2n plus 1. And so integrable submanifolds have rather low dimension compared to foliations, for instance. So foliations you might have much higher dimensional integral submanifolds. Okay, so I should say since I work in the contact category, I should say what a contact homomorphism is, or an isomorphism in the contact category. And I say that two contact manifolds are isomorphic or contactomorphic if there's a diffeomorphism between them such that this field of hyperplanes is mapped to this field of hyperplanes. And in terms of forms, which I usually do, I just require that the pullback of the defining form is defining form for the other, but times some non-zero function. So maybe I should point out at this point, if I fix a contact form, then the kernel defines the contact structure, but if I take a multiple of this form, I have the same kernel. And so there's some non-uniqueness for the forms, but not for the structure. Okay, so then we come to this very basic theorem, and that tells us that every contact manifold locally looks like this example that I showed first. So everything locally looks like that. You can always find a contactomorphism to that one. And so in particular it means that everything is locally the same, so there are no local invariants. So it's very different from Riemannian geometry, nothing like curvature. Now, so anything that will be interesting must come from something more global. And now, so you could look at non-compact contact manifolds, but let's look at compact contact manifolds, because there you see this phenomenon maybe better. But locally they're all trivial, but globally there's still something interesting going on. So here's one way to define the contact structure on S3, which does not use this form definition. So S3 can be seen as just the unit sphere in C2, and so you have the complex tangent planes. You have just a complex tangent space you have the tangent space to S3, and you can take I times the tangent space and now take their intersection. That describes the contact structure. So you have some idea how some other definition of contact form, and so of contact structure. And so let me point out that this is a little bit more general than this construction is a little bit more general than here, because it does not only apply to S3 in C2, but it applies to, if I take a Stein manifold and I take a level set of a pure subharmonic function, then this argument applies. So regular level sets of pure subharmonic functions on Stein manifolds carry a contact structure in this way. So then you have lots of examples. Now there's another class of examples that I want to describe, because it's basically half of the title of my talk. So it requires the following. So let's remember what a symplectic manifold is. So that's an even-dimensional manifold with a closed non-degenerate 2 form. And it has, well, this non-degenerate means that omega to the nth is non-zero. So that's kind of the same as this, very similar to this contact condition. So basic examples are R to n with this symplectic form, or, well, cotangent bundles. This is kind of the universal example. And of course, well, scalar manifolds if there are any complex geometers. Okay, so now what is the relation between symplectic and contact? Well, here's one relation. So take a symplectic manifold and take a hypersurface. Now suppose that there is a vector field that is transverse to this hypersurface, and that expands the symplectic form in this way. So the Lie derivative of this vector field of the along the vector field of the symplectic form is the symplectic form. So you have exponential growth of the symplectic form along this vector field. Then you call such a vector field, you call this Liouville vector field. And it turns out that this is just plug in, basically, that if you have a hypersurface and a transverse Liouville vector field, then this hypersurface is automatically contact, and you get an explicit contact form. And so, well, if you just apply it to these examples, you can write down explicit Liouville vector fields. So in the case of S2n in R2n, S2n minus 1 in R2n, the Liouville vector field is just a radially outward pointing vector field. And you need to normalize it to make sure that this condition works. And similarly, unit cotangent bundles inside the cotangent bundle are also almost always contact. So that gives us lots of examples. And so now I want to go to, well, okay, so this gives me the definition of fillability. So if I have a symplectic manifold, say compact, with boundary, and if the boundary is, if there's a Liouville vector field pointing outward and transverse to the boundary, then you call this symplectic manifold a filling for the boundary. And so let me point out, every example I've written down so far is in this sense fillable, because you just take, well, in the Stein case you take sublevel sets, or in R2n you just take the disk, or for unit cotangent bundles you take, well, just the unit disk bundle as filling. And okay, so I repeat this statement here another time. So, okay, so now you could ask yourself, if everything that I've written down so far they're nice examples, but if they're all fillable, are there non-fillable ones? So this will be the point of the talk. So, well, historically, Gromov found a reason, an obstruction to fillability, and actually you could say that most contact manifolds, in some sense, are non-fillable, but the nice contact manifolds tend to be fillable. It's a bit strange.
When you say fillable, you mean strongly fillable?
Yes, I mean always strong. Yes, so there's another notion, which is, there's a different definition. But then the rest of my talk you need to wiggle around more technical details to make it work.
So you will refer to this one?
Yes, I will refer to this one. And so there's another notion which is slightly weaker, but forget about it. Okay, so now I want to point out that contact manifolds have, well, they're related with symplectic geometry, of course, but they also come with a nice dynamical system. And so, okay, so what do you need? You need a contact manifold, but suppose that you really have a contact form, not just a structure. If that's the case, then you can define the Reeb vector field with these two equations. And actually, if you're familiar with Hamiltonian dynamics, then the Reeb vector field is just the reparameterization of the Hamiltonian vector field. But okay, if you're not familiar with it, just forget about it. So then, in the latter case, let me point out that the Reeb flow on the unit cotangent bundle, so this is a very natural example, is actually the geodesic flow. So then you have some idea what this Reeb flow looks like. But now the bad thing, as I told you, I can define this dynamical system given the form, but the structure does not determine the form uniquely, and so if I take a different form, actually the dynamics will change also. So this is not so nice, but it just happens. And here's a picture of some complicated Reeb dynamics. Well, it's basically there to fill the page. It's just to look nice. It actually represents the well, this is a Reeb flow, but it represents the dynamics in the three-body system. This three-body problem. So this is actually something you could translate in contact topological language. Okay, so here are some reasons to study contact geometry. So the first reason is a very bad reason, but it's the easiest to come up with. So foliations are of course very nice, but typically a form defining a foliation is very special. And so I want to point out that contact forms are the opposite of foliations in two ways. So they are not so nice that the integral submanifolds are not so nice in that sense, but most forms are automatically contact. So outside codimension 2 or codimension 1 submanifold, any form, generic form, is contact. Then, okay, so this is a much better reason. There are strong relations with symplectic and geometry and complex geometry. And okay, so here's an important question. So does every contact manifold admit a periodic Reeb orbit? So this is known. This problem is known as the Weinstein conjecture. And of course, this is important because it's basically rephrasing. You can rephrase the question as: are there periodic orbits in Hamiltonian systems if they are nice enough?
You see that the Reeb field depends on the choice of alpha.
Yes, that's right.
Conjecture, is it that for there exists an alpha?
No, it says for every alpha it should be true. Yes. So okay, so maybe I should rephrase this. So if I take any non-vanishing vector field on S3, then it does not follow that there is a periodic orbit. So there's a rather difficult construction of a non-vanishing vector field where there's no periodic orbit. But Reeb vector fields, which kind of are dual to this contact form, they are not just any vector field, non-vanishing vector field. They are kind of special. So the claim is there's always a periodic orbit. And so this Weinstein conjecture has been proven in dimension 3. So it's maybe interesting to point out. Now there's another application. So this is a very central question in contact topology. So we have this construction. So if you have any smooth manifold, then the unit cotangent bundle of this smooth manifold always carries a contact structure. And so now you can kind of, from that you get if you want, a kind of functor from the smooth, from the smooth to the category to the contact category. And the question is, how much does what does this thing measure? So let me point out one particular question. So if I take two manifolds that are, say, homeomorphic but not diffeomorphic, so a typical example would be S7 and S7 exotic, then we can look at our unit cotangent bundles. Well, the unit cotangent bundles are always diffeomorphic, but the question is, are they actually contactomorphic? And so the hope is no, but it's very hard to actually do something with this problem. So the question also has you can also translate the same question in the symplectic version, and in the symplectic version it's now known that it's actually there is some additional information. The symplectic structure remembers something about the smooth structure, so that's quite interesting, I think. Okay, so now let me tell you how this invariant of contact manifolds works. So we have already seen that psi d alpha is a symplectic vector bundle, so we can find a compatible complex structure. So that means that we plug in this complex structure J into the second slot of d alpha, we get a metric on the contact structure, and so we get a complex vector bundle, and then we can just define the Chern class of a contact structure as the Chern class of this complex vector bundle. And of course I should point out that this construction does not, the resulting Chern class does not depend on the choice of a compatible complex structure. And okay, so what happens, well, you certainly can distinguish some contact structures with this construction, but with this invariant, but there are many that you cannot say anything about. And well, again, this Weinstein conjecture, and in particular, how does the number of orbits depend on the choice of alpha? So maybe I should here, because it's very short, and so I cannot really give nice examples, but let me point out that if I just take the standard contact structure on S3, so the one that I described in these two ways, then every Reeb orbit is periodic. Now I can, instead of taking this round sphere, I can take an ellipsoid sphere, and then there are only two periodic Reeb orbits. So it's the number of orbits is kind of, it can drop dramatically. Okay. So the invariant that I'm going to describe is known as contact homology, and so the short version is contact homology is a kind of Floer homology for a certain action functional. So maybe I should ask at this point, who is familiar with Floer homology? No, okay. Well, and if you're not familiar with Floer homology, then probably you're also not familiar with Morse homology, because Floer homology is kind of Morse homology for some, well, in an infinite dimensional setup.
First, know with Morse homology, and then you have with Morse. So you couldn't know Morse before, right?
Yes, but I think that's true, of course. So that's true, but the correspondence is usually everyone who knows Morse knows Floer, or has heard of it.
I just told my student Morse theory, but I don't think they know.
No, but Morse homology. I'm not talking about
homology. What is Morse homology?
Yes, exactly.
It's not the Morse theory.
No, it's not. It's not. You cannot find this in the book of Milner, if that's what you're asking.
No, but you can find in Wiesen's papers.
Yes.
Okay. Well, that I already told them.
Okay. So then I was wrong. Okay. So anyway, let me then briefly remind you of, or tell you about this. So I'll describe first Morse homology. So this is kind of the prototype for all these Floer homologies. And so the setup is always the same. You take a space, you take a function, and you set up an homology theory using this data. And so the Morse homology is the finite dimensional version, and this is the one that you can at least visualize. And most features that you need for the Floer version are already here. So we start with a space. In this case, we take a compact manifold M. So I take here just S2, and I take here this funny embedding and another standard embedding. And the reason for that is that the second thing that I need is a function, a Morse function. And so I get two Morse functions on S2. So to consider Morse homology, you just need one, and you take you define a chain complex of Morse homology as the graded Z2 vector space generated by the critical points of this Morse function. So in this case it would be a 4-dimensional vector space, and in the other case it would be a 2-dimensional vector space. And the grading is given by the index of a critical point. So that's the number of negative eigenvalues of the Hessian. Okay, so that's then given. Now, how do you define a differential? Now, for that you need some additional data, namely you need a metric. So you take a metric on M, and then you can write down the flow equations for this complex. And so it's just an ordinary differential equation. In this case, you take the gradient with respect to this metric of this Morse function, and then you can look at flow lines. And well, since the gradient you always go down if you want in this case. If you follow the gradient line to -infinity or to infinity, you always have to end up at a critical point. And so these are the boundary conditions. So we're looking at an ordinary differential equation where if you follow back to -infinity, we get some critical point A, and to +infinity, we get some critical point B. Okay. Now, we collect the solutions to this flow equation in a moduli space, which I will call MAB. So these are the solutions to this flow equation and up to reparameterization. So here I want to point out that if I have a flow line, so if xt is a solution, then xt plus a constant is also a solution, since the boundary conditions are not going to be changed. So it can just reparameterize by shifting it in the time. Okay. Now, if my metric, if the gradient vector field is sufficiently nice, then this moduli space is actually a smooth manifold of dimension equal to the index of the critical, index difference of the critical points minus 1. And so sufficiently nice means more smil, but as you see in the example, here this works. So here the index difference between these two critical points is 1, and there's exactly 1. And here there are 2 orbits, but you see that the moduli space is a nice finite dimensional manifold. Okay, now maybe I should go back to this picture. There's one problem though, and that is if I look at the moduli space of flow lines from A to D, then you see that it's actually not compact, because you have this, then if you move a little bit more, then you go like this, and you see that if you move your point closer to this flow line, it starts to look not like one flow line but like 2 flow lines. So that's what you will do to compactify the moduli space. You will add broken gradient trajectories. So that's a finite sequence of flow lines. And okay, so that's how we compactify the moduli space. And then let us then define the differential. And we define the differential simply as saying any critical point, so the generator of this Morse homology, goes to a linear combination of critical points where the coefficient... Yes.
Compactification is still smooth?
Yeah, it's a well, it could be manifold. It's manifold with corners in general. So, well, so in this example, if you want, this moduli space from A to D before the compactification would be the open interval, and it would be the closed interval afterwards. So that's nice, I would say. But if you have more critical points, you get something maybe a little bit less nice than that. Of course, in 2 dimensions, that cannot happen. But yes. Okay, so that's the differential. So maybe in the example you can see, of course, that the differential is really a differential, because if I take d of this one I get c, and d of this one I get this one plus this one, but then work mod z2, so it's 0. However, there's a more general argument. So d squared is always 0. And why is that? Well, what does d squared count? D squared counts flow lines that go first to some critical point and then to some other critical point. But now, so if I go from A to B to C, I can regard directly the moduli space from A to C. There's index difference 2, so it's a one-dimensional moduli space. And now I can look at the boundary of this one-dimensional moduli space, and there I will find broken gradient trajectories, which are counted exactly by d squared. So that's the idea, because the boundary of one-dimensional manifolds are either, well, what are one-dimensional manifolds? They're either S1 or an interval, a closed interval. And so mod 2, the number of boundary components is always 0. So that's why d squared is 0. You can do this also with z coefficients, but then you need to take care of your orientations. And I don't want to talk about that. Okay, so we have now that d squared is 0, so we can define a homology. And I claim that the homology is an invariant of the manifold M. And so I'll go back to this example, and so you can compute here explicitly and find that you get the same answer. So it's actually a theorem, and I hope to convince you with just an example. Okay, so now the next step is to follow this scheme, but now for different functional and a different space. So the new setup is, okay, we start with a compact contact manifold, and then with form, we need to have a form, and then we look at the space of smooth loops in M. And as function we take well, this functional, we map every smooth loop to the integral over alpha. And you can check that critical points of this action functional are, well, reparameterized Reeb orbits. If I lie a little bit, but they correspond to periodic Reeb orbits. So now you might ask yourself, if I do Morse homology, I actually really need a Morse function. I kind of jumped over it, but if you take something well, which is not Morse, then bad things happen. And the same is true here. I'll just run over this detail and pretend that it does not happen, but it's very important to take a decent functional, and here decent functional means a decent form. So I claim that you can always find a contact form for which the Reeb orbits are are non-degenerate. You can work out what it means to be non-degenerate. You can compute the Hessian, and then actually it's a bit dirtier than you might expect, because there's always some degenerate direction, but things will work. Okay, so now so we are in the same setup, and we want to copy everything at first. So we define a chain complex as a free module generated by the critical points, so by periodic Reeb orbits. And we define the grading as the grading is defined by a so-called Condit-Seder index. I won't define it because it takes time to define, and this is actually a point. So up to this point you could say it's completely analogous, but this is not the index of a critical point, because the indices of this function, the critical points, how do I say this? The unstable and stable manifolds are infinite dimensional in this case, so there's actually no real index to talk about. So you have to replace it by something else, and this will do the job, but it's not so nice. Okay, but suppose that we just believe that this works somehow. Then we
always define, right? This index.
The index.
Yeah.
What do you mean? The Condit-Seder index.
Yes.
Yeah, you can define it.
It's always defined. In every situation, or you need a restriction?
No, you need a restriction. If you say Condit-Seder index, you actually need the non-degenerate periodic orbits, in the sense that the Poincare return map along the orbit has no eigenvalues equal to 1.
Okay.
So there's a restriction. Now you can generalize it that there are no restrictions, but then the index is no longer integer.
Yeah, but then if you have that non-degenerate condition, then you always can define
yes.
manifold.
Yes, you can always define this index. Yes. Okay, so the next step is to define the flow equations, and for that we need a metric. And this is a bit dirtier than before. So we fix a compatible complex structure for psi. And then we get a metric on M by saying, well, the Reeb field should be orthogonal to the contact structure, and and we get a metric on the contact structure itself.
I asked that question because for the case of symplectic manifold, then sometimes you do not have that Lagrange intersection. Sometimes you have different paths have different index.
Yes.
Cannot have globally defined Morse function. It's like
so here
in circle. So, but this case it doesn't occur, right?
Yes and no. So if so if M is nice enough, say simply connected, then okay.
Right.
But if it's not simply connected, then it doesn't work, because this Condit-Seder index is actually it's defined as a kind of winding number of a path of symplectic matrices. Now that's nice, but to get a path of symplectic matrices I need to trivialize the contact structure, and there's a good way to do this. Just fix a spanning surface, then you trivialize the structure over the spanning surface, and then you get something. And it does not depend, if the Chern class is not 0, then it does not depend on the choice of spanning surface. But if the Chern class is if the Chern class is 0, it does not depend on the choice of spanning surface. But if the Chern class is non-zero, then it actually depends on the choice. And if your orbit is not even contractible, or doesn't span, or not trivial in H1, then it's basically up to you, the index. So then only index differences make any sense, and then still you need to keep in mind that the Chern class is actually, so then you need to take actually a different coefficient ring, and So you need to introduce a graded coefficient ring, but this just complicates the story, so just take the nicest situation where everything works.
So what's the nice situation? Simple connected?
Simple connected, Chern class 0.
Okay.
Otherwise it's not so nice.
Oh, the first homology is general, then maybe okay.
Yes, that's also okay. But the simplest is okay. Yes. So there's actually a disadvantage. Okay, well, I'll just continue and point out the other problems later. Okay, so we have now a metric on M. So you get an L2 metric on the loop space, and then you can take the gradient of this functional with respect to this L2 metric. You just compute bluntly, and you get a partial differential equation. And let me point out that you don't use that partial differential equation because it's a PDE for a cylinder on M. And so, of course, with the asymptotic boundary conditions, but it's M is an odd dimensional manifold, so you get a PDE of some not well-known type. However, it looks like a Cauchy-Riemann equation. It's very similar, and it's kind of what happens is that you project out the part, you project to the contact structure. There, it's the Cauchy-Riemann equation. But in the part not in the contact structure, it's something else. So that's not the PDE you want to work with. So what you do instead is you extend this flow equation to R times N. And on R times M you have a genuine complex structure defined on the whole tangent space just by using this definition. So you extend the complex structure this way. You say that J times ddt, so the R direction of this what's called symplectization, R times M, you say that J times ddt is the Reeb field, and if you say that J times R is minus ddt, you have extended the complex structure. And then you get a genuine Cauchy-Riemann equation for a cylinder, so that's this, and you get asymptotic boundary conditions. There are now asymptotic boundary conditions in this sense that if I follow the cylinder up to infinity, then I get one critical point and I get another critical point at the other end. Okay. So we just keep copying the Morse homology. So we define a moduli space as solutions to this flow equation up to reparameterization. And now there is a dimension formula and it has this form. So let me say something about this. So there are now a bunch of problems. So first of all, before I claimed that this moduli space of trajectories between critical points was a smooth manifold, and for that you needed some mild condition. You needed the gradient vector field to be more small. But here it's kind of since I don't want to say something that's not true, it's best to say nothing at this point and just pretend that it's a manifold. There are situations where it's true, there are also situations where it's not true. And this dimension formula is actually just the Fredholm index of this problem. And so if this manifold is smooth, it's actually the honest, it can be the honest dimension, but there are some complications. Just for the purpose of the talk, just pretend that this formula is true. So here I mod out by R, and why do I do that? Well, I mod it out by reparameterization in domain, but since I extended the equation also in the target, I added this R factor, I have an additional symmetry which I have to mod out by. So the formula formally looks completely similar to the formula before, but this -1 is due to modding out in the target, whereas before it was due to modding out in the domain. So it's actually not the same, but it just looks the same. Okay, but if we just accept this, then everything looks very similar, so you can try to define a differential in the same way. But there's an additional problem, namely compactifying the moduli space. So before, if I took a sequence of gradient trajectories, a sequence of gradient trajectories always breaks as a finite sequence of gradient trajectories. But if I take a sequence of holomorphic cylinders, there is absolutely no reason that it needs to break as a pair of cylinders, which is what you need to happen if d squared is going to be 0. So it does not happen. So in general this could happen, or other things could happen. Now, okay, so I call this bad breaking if this happens, but still we can compactify the moduli space by adding these so-called holomorphic buildings. So a holomorphic building is a finite sequence of holomorphic curve in the symplectization with matching asymptotics, and they arise as limits of a sequence of holomorphic curves in the symplectization. Okay, so anyway, so we define a differential, and like in Morse homology, it's action decreasing. It's because you go down the gradient flow, and so it's just I copied just the definition. And let me point out that if there is no bad limit behavior like this, so if every sequence of holomorphic cylinders breaks into nice pair of cylinders, then we can define a homology theory, and this homology theory is an invariant of the contact manifold. Okay, so that I'll call this homology theory cylindrical contact homology. Now, okay, this is not very nice because I have to add lots of assumptions to have a theory that is defined only in very special cases. So let's try to solve it. So what's the?
So this, what is something you mean like? Doesn't break into.
If I take a. So yeah, so if there are no holomorphic planes, then you're safe. That's okay, but no holomorphic planes is kind of hard to exclude. So the simplest way to have no holomorphic planes is to say there are no contractible Reeb orbits, but then I start to contradict what I previously wanted, so it's kind of it's not so nice. But yes, this would be one situation where there's no problem. So in general, if you believe the index formula, then you can also look at this picture. So what happens? We are interested in one-dimensional families of holomorphic curves, which means index 2, index difference 2. So this has index difference 2. Now this 2 is the Fredholm index, and the Fredholm index is additive, so it needs to distribute over these two things here. Yeah. But if I assume that all moduli spaces are cut out transversely, then for a holomorphic curve to exist, the index must be non-negative. So I need to write 2 as a combination of 0, 1, and 2 in here. So I can say this has index 2 and this 0, 0. But index 0 in the symplectization actually means it has to be a vertical cylinder. Because if I have a plane, then I automatically get a one-dimensional family by translation. So here cannot be a 0 because it contradicts translation invariance. So this could be a 1 and here a 1 and this is 0. That would be bad limit behavior, but if this is index 1, then this Reeb orbit has index 1. So if I compute all Reeb orbits and there are no Reeb orbits of index 1, then d squared is 0. But that's under the assumption that all moduli spaces are cut out transversely.
But that you can do, right? You can always.
No, you cannot do it.
Not do. Oh.
So you can do it if the holomorphic curves are what's called somewhere injective, meaning that they're not multiple covers of something.
Right.
But since my chain complex includes, I include all periodic Reeb orbits, including multiple covers of Reeb orbits, so I cannot.
So you need a more powerful perturbation.
Yes. Okay, but I won't talk about that. So let's try to get rid of this bad breaking problem. So what's the problem of a bad breaking? If I have a sequence of cylinders, it does not break as a cylinder. But this is solved by the following very simple idea. If I have a family of trees, a sequence of trees, then a sequence of trees breaks as a tree. So what I want is to count, in the differential I want to count trees. So what I do is I'll kind of upgrade my chain complex and I'll define it as a differential graded algebra generated by periodic Reeb orbits, and elements of this algebra are just finite sums of products of Reeb orbits. And then I define the differential on the generator as just the count the number of zero-dimensional families of trees, connecting gamma A to, a bunch here. So what do we count in this differential? Well, we count certainly cylinders just as before, so that's just the same term as before. We count also planes, if there's if there's a rigid plane, then we would count this. So this would this would correspond to the bad breaking term before, and we count also things like this.
Is it algebra?
What?
Is that commutative algebra?
Yeah, graded commutative.
Graded commutative.
Yes.
Degree of.
Yes.
What's the degree?
Degree is still conditioned index plus a shift. There's a shift just to make sure.
Have an absolute degree?
Again, if I assume what is it, H1 is 0 and C1 is 0, then yes. So in general, if there you can, well, H1 is 0. If you're willing to work with a weighted coefficient ring, then H1 is 0 is enough. Okay. So we count now these kinds of objects. And so, modulo all these transversality problems, we get the following theorem. So we have a differential graded algebra with a differential, and the homology of this differential graded algebra defines an invariant of the contact structure, and we call this contact homology algebra. Okay, so let me point out that if this theory has sufficiently many generators, if this homology has sufficiently many generators, then a contact structure must have periodic Reeb orbits no matter what form you take, since it's an invariant. Okay. However, I'm interested in the question of fillability, and for that it's useful to look at the following notion. So let's look at a degree-preserving chain map from the algebra, from the chain complex of contact homology algebra to the coefficient ring. So say Z, but in general just something else. And okay, so we have a chain map, so we just have this property. And I want to point out that if I have a strong filling for a contact manifold, then we can define an augmentation by just counting the number of planes bounding an orbit. So I take here a generator, I send it to the coefficient ring by just counting the number of planes bounding that orbit. So it's zero in all degrees. It's only non-zero in degree 0. In all other degrees, they come automatically in 2 high-dimensional families if I have transversality.
How do you give degree to R?
The coefficient ring just has degree. So if C1 is 0, then it has this degree 0. If C1 is not 0, then it's basically the degree depends on the homology class. On the homology class of the so you have a.
What is R?
R is the coefficient ring.
It's a ring. It's a ring, right?
Yes.
Like what?
Well, usually Q,
okay.
Or what you often take is Q, the Novikov ring.
Oh.
Something like this. This is R. Okay. Okay. So let me give a sketch of the argument here. So the argument I will give only works, well actually what I wrote down only works if it's not just a strong filling but an exact filling. So what's the idea? So why do we get a chain map? That's the main problem. So let's look at a one-dimensional family of planes in the filling. Then such a one-dimensional family, we compactify and we look at the boundary. So what does the boundary consist of? Well, the boundary consists of things like this. So something in the symplectization and something rigid in the filling itself. But this is exactly epsilon composed with D. And on the other hand, it should be 0 because we are counting the number of boundary components of a one-dimensional manifold. So this gives our identity. Now, okay, this brings me to the following notion, which sounds completely ridiculous at this point. We call a contact manifold algebraically over-twisted if it has vanishing contact homology. So let me point out that what does this notion mean? If the homology vanishes, then there cannot be any augmentation. Because if there is such an augmentation, then on chain level it sends 1 to 1. On the other hand, if the homology is 0, then 1 is exact. So 1 is the bound is D of some combination of Reeb orbits. So in the homology it's 0, but 1 is not 0 on the right hand side. So then you get nonsense. Okay, so that's the ID. So if the homology is 0, so the homology algebra is 0, then there cannot be an augmentation and therefore no filling. So this is the obstruction I aimed at in my talk, in the title of my talk. So let me point out that that such algebraically over-twisted contact manifolds, so it's vanishing homology algebra, they actually exist by an explicit construction. And so the idea is, very briefly, you take a so let's just draw a picture. So in dimension 3 you can take a knot, and you look at the contact structure on a knot and on a neighborhood of a knot, and then the contact structure you can write down explicitly, and so you have maybe a nice contact form of the form, say this is the z direction, and I use polar coordinates on this disk. So this is the r direction and this is the theta direction, and then I get dz plus r squared d theta. And I replace it by just something else. So what happens here is, what does this thing do? The contact structure rotates like this, and I replace it by something that rotates like this. And if I make a full turn, I come back at the same way. So near the boundary I don't see any difference, but in the interior it twists. That's, if you want, that's one reason for the name over-twisted. But if this happens, then you find new generators for chain. So you change the contact structure, you find new generators in the chain for contact homology, and you actually see that the homology vanishes after this operation.
What's the dimension of the manifold?
It works in any dimension, although in dimension 3 the construction looks like this. In higher dimensions the construction is considerably more.
So the structure is over-twisted, or if the dimension is
over-twisted. So what is it? So
what is the relationship between over-twisted and algebraic over-twisted?
So the relation is, over-twisted implies algebraically over-twisted. So this construction is, after this construction there is, so this construction yields what's called an over-twisted manifold for, I can give a definition, but if you look at the construction that's maybe one motivation for the name. And so this is the relation in dimension 3. In higher dimensions this notion is not defined. So, but this you can define. So that's that's something you can try to do to look at. So there's a whole story about this. Namely, in dimension 3, over-twisted manifolds are classified, whereas non-over-twisted ones are not classified. So the hope is that if you divide contact manifolds in these classes, you can understand them in a better way.
What about the other direction?
It's unknown, and at the moment the suggested proof is so horrible. The suggested proof is basically classify 3 manifolds and check by hand for all that it's true.
Wait, you believe this is true, right?
Yes.
I see.
But there's no so.
The 3 manifold is already classified, right?
Well, no.
Well, I thought it's classified by pyramid or something.
Oh, Perelman just says that every simply connected 3 manifold is homeomorphic or diffeomorphic to S3.
No, this is geometrization conjecture.
Yes, but that still doesn't. Okay, so then there's still some work to classify the 3 manifolds to really give them in a list.
Not for you. I mean, you need a kind of classification.
And I need more than that.
Okay.
Because so.
Part is not classified.
What is it?
I think about the contact structures, hyperbolic parts.
Yes. So hyperbolic 3 manifolds, whether they admit the tight contact, so a non-over-twisted contact structure or not, is unknown.
Yeah, of course.
So every contact manifold admits an over-twisted one, or in every. Yes.
How do you show that theorem? So you show that by showing that is it over-twisted or?
No. So what I do is the following. Okay, so in dimension, let's give the argument in dimension 3. So you replace this by this contact form. So you take S1 times D2, and then you take the form H1 R dz plus H2 R d theta, where these functions H1 and H2, well, they are going to model this twisting behavior. So H1, H2. So it's very dangerous to draw this. So something like this should be H1. So just to make sure that it kind of looks like the same at the end. And for the other, it should grow quadratically here. And then, well, you replace it by something that looks like. Now I don't end the right way. Something like this, say. So now you might not say, well, what does this mean? This is just some bunch of functions. So I should point out that the Reeb vector field is this form.
You are trying to use the Lutz twist.
Yes, I use a Lutz twist, but I actually don't care about the Lutz twist. I actually care about the Reeb vector field, and this is this form. So it's now getting automatically kind of not so nice, I would say. So the point is, if H2, this is H2, if the derivative of H2 is 0, you find a Reeb orbit that that goes like this. So the picture is, if this twist, the Reeb field is kind of transverse, so say orthogonal if you cheat a little bit. So there's a point that stands like this, and then the Reeb field looks like this, and you find a periodic Reeb orbit. And this Reeb orbit has the right index to kill contact homology. And okay, that's the first observation. The second observation is this Reeb orbit bounds a disk, obviously, and this disk lifts to a plane in the symplectization. And you write this, so you write it down explicitly. So you just write down the formula. And since so of course in general the Cauchy-Riemann equations are very nasty, but actually here, because everything is symmetric, you plug in some gas solution, and then this PDE becomes an ODE, and you solve it explicitly, and everything works. You can check transversality by hand, because the symmetry allows you to do to compute everything. So the details are not nice, but the idea is very simple. And so then you have a plane. So you have a differential. So the differential. So I want to argue then that the differential of this orbit is 1. So for that you need to show that this. Okay, we have one plane. You need to show that this plane is unique, and that there are no other holomorphic curves. But it's not so difficult actually. It took me a long time to work the details out, but it's very basic in a sense. Okay, so I can continue a little bit, and so now I'll move into territory that I'm not so used to. So this is what I do, but let me point out a generalization of this theory, which I'm not familiar with, or not that much. So so the idea is the following. So we have this graded commutative algebra, and the first thing you do is, sorry. Yes.
So what was the application of your result?
Well, so there exist non-fillable contact manifolds in any dimension. That's the.
So any contact.
Well, actually, what I can do is, given any contact manifold, I can modify the contact structure, really not the form, but the contact structure.
Okay, sorry. Yeah. Go ahead.
Yeah, and this new modified contact manifold has, so it's diffeomorphic to the old one, but it is vanishing contact homology, so it's not fillable or not strong.
This new contact structure is different from the old one.
Yes.
So you're just saying the same manifold there is.
Yes. Okay, so now this upgraded invariant, and so let me go through this so quickly. So the first observation to make, well, this is something very stupid. So before we have an algebra generated by periodic Reeb orbits, and you usually call them gamma, and the first idea is to call them Q. So this seems no difference at all whatsoever. But if you have Q and you have P, then you think of maybe Heisenberg algebra, and that's actually the right motivation. So what's the idea? So we still have the same algebra. I just call my generators Q, just for formal reasons. So what I want to do now is I've copied here the differential for contact homology algebra, and I just replaced the gammas by Q gamma. So it's just the same formula. But the last term I interpret, well, I just formally write 1 as the derivative of that. So I can interpret this, if I now just take it out, as a vector field. So it corresponds to a Hamiltonian vector field of a certain Hamiltonian that's linear in P. And so we restrict them to the 0 section if you want. So now we are looking at some formal space where we pretend to have some symplectic form. But okay, so this is the first point of view, but we can also just look at this differential operator and say, well, what have we done so far? We have an homology theory counting where we count holomorphic curves, but we only count rational curves. And we count only rational curves with one positive puncture, because we want this tree structure. So let's replace this by something where we count everything. So what's the idea? So now we have this notion of BV infinity algebra, and it consists of the following. It consists of a graded commutative algebra, so that's basically the same graded commutative algebra that you already had. Okay, and then we can define a differential operator on, well, just take power series in H bar with its coefficients, elements of this graded commutative algebra, and the differential operator should have square 0, so it should define some homology, some differential. This differential operator you should be able to expand it in terms of something like this, where this is a differential operator of order k, and d of 1 is 0. So okay, so this is just general definition of this notion. And so in the setup of symplectic field theory, what you do is you can just specify this one, and there's an explicit formula. This is the formula. So we take here a number of derivatives, and we count now more general moduli, elements of more general moduli spaces, and there's some combinatorial factor here. So we count now holomorphic curves with genus and multiple punctures, all kinds of things. So let me point out that D1 is just the previous D the previous differential that we already had. And now this is from Algebraic, Differential, and Hofer. So this is, well, theorem. So every theorem should be modulo lots of assumptions, but they state it as a theorem in their symplectic field theory paper. So if I define dk as above, then the previous graded commutative algebra, so this commutative algebra, this graded commutative algebra, now with this new differential is a BV infinity algebra. So it has these features as before, and okay, so d squared is 0 in particular, and this equation is known as the master equation. And so what happens is that if you compose differential operators, then you take care of all possible gluings. So let me just point out some pictures. So this term would correspond, so the term in the differential counting a pair of pants, a rigid pair of pants, corresponds to this quadratic polynomial in the first two terms and then the first derivative. If I want to have something like this, I have just two derivatives here. Now the motivation for this SFT stuff comes from the following. So this is a kind of dream of Algebraic, and I don't want to try to prove this because this is impossibly hard. So the idea is, well, let's try to count the number of holomorphic curves in a complex or symplectic manifold. So that's in general very hard. So maybe you can simplify it by cutting my complex or symplectic manifolds apart along hyperplanes, certain, say contact type hyperplanes, hypersurfaces, sorry. And now, okay, so now I have simpler pieces that I hopefully can understand, but I need to glue them together to get the original manifold. So what does gluing together correspond to? Well, this corresponds to gluing these holomorphic curves, but these glued holomorphic curves are counted by this SFT setup. So what does this to do with fillings? Well, we have seen this notion of algebraically over-twistedness. So if I reformulate it in this new language, it means that well, this D1, which is basically our old differential, is 1. And so I define the notion of algebraic torsion if this h bar to the k is exact, but h bar to the k minus 1 is not exact. And this also implies non-fillability. Basically, the argument is that there cannot be a map from a non-zero map from something with torsion to something with not torsion. So this would be algebraically over-twisted. If there are things like this, then you have one torsion and then you have two torsion. And you can also construct such spaces. And okay, so this is, many people try to do these things. So genus is impossible so far. To work with genus is so far impossible.
Genus?
Yes, so there are never transfers. But okay, so what I want to point out is there are lots of obstructions in this theory, although this is the only one that I feel kind of comfortable with. But there are many other obstructions. And
who first defined the notion of algebraic torsion?
Wendell, Latchev and Wendell. Janko Latchev and Chris Wendell. Okay, so that's let me finish my talk here. Already over time, or not, depending.